Yeah.
So there's an exponential loss of energy then. So it's losing more and more energy as they get closer and closer.
It's losing more energy as they get closer and closer, but not very much happens. So the physical scales involved are pretty low until the final merger, and then a really dramatic thing happens. Horizons merge, the space-time is highly curved, and all this gravitational radiation gets emitted. Yeah.
So as these black holes are emerging, they're losing mass at the last hundredth of a second, or actually even thousandth of a second, probably have a huge influx of it or outflux of energy.
Right.
In the form of gravitational waves. You have a loss of mass, and so that mass is directly convertible into gravitational waves.
Yes.
Okay, so or some other kind of energy. Although I'm
mainly gravitational waves.
From what I read before, was not aware if there was any neutrinos or gamma rays from that event. But if there was, it's probably pretty minimal. But at the same time, the gravitational waves are being released. If there's a loss of information from the black hole, from the event horizon, would you be looking at that information also being in a form of actual space itself? And could you then link that in some peculiar way to Hoyle's steady state theory?
Okay. Let me try to answer the first question, which is whether there was also electromagnetic radiation that was emitted during the merger. And of course, there would be some, because there's some stuff around the black holes, and that stuff, accretion disks, and that matter will collide to some extent, but it's very minimal compared to gravitational waves. That's different from what happened in another collision that we saw, which is they observed a collision of two neutron stars. And neutron stars don't have an event horizon. They have all this matter just sitting there. In the collision, matter smashes, one neutron star smashes into the other neutron star, and you have real matter colliding. That emitted a whole bunch of energy in gamma rays, which was detected in conventional telescopes, in addition to the gravitational waves that were detected with the LIGO device. For these black holes, there's just not much matter around. Basically, by this point, they're basically just pure space-time objects. The thing that happens in the collision is these space-time shapes merge into one somewhat larger space-time shape. So I didn't completely understand the second question, but maybe you can ask later. I want to move on now. So, okay. The goal of the first part of this talk was to impress you. So this makes black holes sound very impressive. They are very impressive. It's crazy scales involved. But that's actually not why they are important to present-day high-energy theoretical physics research. So the kinds of things that people like me work on, that is not why we work on black holes. It's impressive, but it's, I find it cool, but that doesn't really have anything to do with my research. The reason that we work on black holes is different, and there's a risk that it's going to seem kind of boring. So I'm going to try to convince you that it's amazing, but the rest of the talk is going to be harder to find amazing. Let's put it that way. Okay, so let me try to introduce you to the different types of theoretical physicists. I'm not going to get all of them, but I'll discuss three categories. So there are condensed matter theorists, and we have some of them at ACP right now. So the basic problem that condensed matter theorists study is the following question: when you take a lot of particles and let them interact with matter and let it interact in different ways, in particular, in a regime where quantum mechanics is important, what happens? What kind of phenomena can be exhibited by those interacting particles? And an example of the kind of surprising and important phenomena that you can uncover is superconductivity. This is roughly speaking what condensed matter theorists do. I hope the condensed matter theorists who are in the audience will not take offense from this description. Okay, so there's another class of theoretical physicists, general relativists and cosmologists. Basically, what these people study is Einstein's equation. Study Einstein's equation and look at different kinds of solutions, like describing black holes, describing collisions of black holes, describing the evolution of the universe itself, which is a dynamical system described by Einstein's equations. So that's the kind of thing that these people study. And then there's a third category. This includes me, high energy theorists. And the thing that we are trying to understand, roughly speaking, is what are the basic rules, or the basic rules that describe physical reality. An example of something that many of us work on or use in our research is string theory. When it's an attempt to give a mathematically consistent set of rules that can describe our physical reality, that would reduce in certain situations to Einstein's equations and to the rules of interaction for particles. These are three different types of theoretical physicists, and all three of these types of theoretical physicists are interested in black holes. And the kind of thing that ties their interest together is the following concept. It's a duality. So, okay, duality in physics, what that means is it's a kind of secret equivalence between two seemingly different systems. So an example of this, not from physics, but just an example of it, would be suppose you have a movie that you could store on a DVD or VHS. And these are different objects. The DVD and the VHS are very different objects. But if you kind of decode them the correct way by putting them into the appropriate player, then the movie is the same. There's something the same about those two objects, but the abstract information that is stored by them, even though the media are very different. And that's a kind of dualities are kind of like that. Dualities in physics are kind of like that. Two rather different physical systems are secretly the same. The most important duality in physics is called the ADS-CFT duality, or ADS-CFT correspondence. And it was discovered by Juan Maldacena, who is actually at Aspen Center for Physics right now. And what is it? It's the following absurd statement. So the statement is that an interacting system of particles, a particular one, or a particular class of interacting systems of particles, is this kind of thing. The condensed matter theorists study. The claim is that a particular example of that is actually secretly describing a higher dimensional gravitational theory. So something that cosmologists or general relativists or maybe high energy theorists would study. So a system without any gravity at all, just some interacting theory of particles, no gravity, interacting particles, is supposed to be dual in this sense, so secretly absolutely equivalent to a completely different looking system. That completely different looking system is a theory of curved space-time in higher dimension. But that, well, okay, so imagine I tell you this, you say, I must not be understanding what he's saying. It doesn't, I can't like compute this. But that's not, you're understanding what I'm saying. It's just it's an absurd statement. It's an incredible fact that appears to be true. And so why does this mean that these three different people care about black holes? Well, it means that these interacting systems of particles, in some cases, are really describing a space-time. And interesting thing that could happen in a theory of space-time is you're going to have black holes. So there are states of interacting systems of particles that are somewhat related to the types of systems that condensed matter theorists study, but are actually secretly describing a black hole. So if I study a black hole, I can somehow map that calculation, that system, onto some system, completely different looking system of interacting particles. So now the different communities can talk to each other. We can compare our calculations. As matter theorists do some calculation on their interacting system of particles, or they discover some type of qualitative effect. And then somebody studying a black hole can go and try to set up a computation and find the same effect. And it's actually, that's a lot of what happens here at ACP, is they bring in people from different communities, condensed matter theory, relativity, string theory, talk to each other, we compare calculations, and try to better understand this absurd equivalence, this ADS-CFT duality. Okay, so what I'm going to do in the rest of the talk is I'm going to explain one example of that. So the example is going to be a black hole that is implementing a sort of purely quantum mechanics operation. So something that would make sense over here. And I'm going to show you how the black hole does it. All right. Okay, I'm going to try to show you how the black hole does it. So, all right, so the thing that the black hole is going to do is called quantum teleportation. And I'm going to show you some cartoons to illustrate first what ordinary quantum teleportation is before we get to the black hole. So forget about black holes for a minute, think about the cartoons. So before we talk about quantum teleportation, let's talk about something simpler. This one is called communication by shouting. So Alice here has just flipped a coin and she got the result heads. She wants to tell Bob what she got. So she shouts, it's heads. And then Bob says, okay, great. He now knows that it's heads. What if they want to do something a little bit more complicated? Can communicate the same information using something called one-time pad cryptography. The way that works is that Alice and Bob in advance share a code book. Code book has something written in it. It could be heads, could be tails. In this case, it was tails. They have the same code book. So Alice flips her coin, she finds heads. She wants to tell Bob the answer was heads, but she doesn't want to say it explicitly. So what she does is she consults her code book. She discovers, heads is the opposite of tails. So she says, hey, Bob, it's the opposite of what's written in your code book. Bob opens the code book, he says it's tails, he says, okay, I should take the opposite, it's heads. That's one-time pad cryptography. It's actually it's a type of cryptography. Just to make it more explicit, here's what it looks like. Alice takes the result of the coin plus her code book. She spits it into a machine that compares them. It spits out the fact that they were opposite. She says it's the opposite. Bob takes his code book plus the word opposite, sticks it into a machine. Out comes heads. And now Bob knows the answer is heads. Okay. Now you're ready to understand quantum teleportation. Quantum teleportation is the goal. Alice has a quantum state, psi. This is the way we write quantum states, letter, and this funny symbol invented by Dirac. So she says, I have a quantum state. I don't know, how am I supposed to say? I can't shout quantum state. In particular, quantum states are hard to transport. In particular, if you don't know what it is. Alice might not know what the quantum state is. She has a physical system, a quantum computer in a particular quantum state. She wants Bob to have that quantum state. He might not know what it is. If she measures it to find out what it is, he might destroy it. And even if she knew what it is, it might be that he cannot communicate it to Bob because quantum state requires a huge amount of classical information to convey. So it looks like Alice is really stuck. It looks like the only way she's going to be able to get Bob to have the quantum state is actually to physically take the system, has the quantum state in it, and hand it to Bob. It doesn't look like there's any way that she can just communicate to him what the quantum state is. Quantum teleportation is a protocol that was invented in the early 90s that solves this problem. And it's kind of similar to one-time pad cryptography in that it makes use of a pair of code books that are shared by Alice and Bob. Instead of just being a code book that says heads, heads, or tails, tails, these are a pair of quantum entangled code books. So entanglement, that means is that the code books have a particular and strong type of correlation that is possible. In quantum mechanics, you have probably heard about that, about quantum entanglement in previous ACP talks. For our purposes, what's important is that it's a type of state that these two code books that could be in, they're very highly correlated with each other. Highly correlated. Okay, and it turns out that although it is impossible for Alice to call Bob up on the phone and tell him the quantum state without the entanglement, if they have these entangled code books, then she can do it. Then she can send the quantum state. It works. It's very similar to one-time pad cryptography. She takes the quantum state together with her copy of the code book, sticks it into a machine. The machine does some measurement, comparison, which is not too different from what we were discussing before. It outputs a number, let's say 3. Alice just shouts to Bob, 3. He takes the number 3 together with his entangled code book, sticks it into a machine, and out comes the quantum state psi. So that's the structure of quantum teleportation. And it's actually, it's an important protocol in quantum computation, quantum information theory. Technically what it does, it allows you to send a quantum state using classical communication, so just saying the number 3 over the phone, plus a resource that you have to share in advance. The resource you have to share in advance are these entangled code books.